Okay, so to begin with, let's look at some of the definitions and make this a little bigger that we'll have, and we good to go. Okay, so first, what do you think this would be? So we're looking what can be induced by causing a particle to collide with a nucleus. Or actually, let's do that the other way around. Then you guys will have to type a letter if you want to guess. So which one do you think goes with fission? No, it's not G. So for fission, what we're actually looking at is going to be F, which is where it splits in with the bombardment of, sorry, my screen just went black. It does that sometimes. Can you guys still see the right page? It should be working, right? Yeah, it's a split after bombardment of a neutron. So it's going to be F. Right? What do you think a mass defect is? D, perfect. That is D. The difference between the mass of the isotope and the mass number. Nice job. What about activity? B, perfect. So it's the rate at which a sample decays. What about nuclear transmutations? It's going to be A, perfect. So it can be induced by a particle colliding with a nucleus. What about fusion? So fusion is like kind of the opposite of fission. So it's like earlier you guessed G for fission. You just had them backwards. So G is fusion. So fission is where one bigger molecule is going to separate out into two smaller ones, and fusion is where two smaller ones are going to come together to form one bigger one. And with either one of those, they can produce a rather large amount of energy. But and so we can use those to do that. What do you think critical mass is? E, perfect. So that's the minimum mass that must be present for a chain reaction to be substituted. So if you looked at the PowerPoint, one of the things it talked about was in various like radioactive bombs, they'll have two smaller amounts of the mass, but something that's preventing them from colliding. But then to like make it actually explode, it's gonna they'll end up going together, so it'll reach that critical mass. And what about particle accelerator? See, nice job. So there are the atom smashers, which are enormous machines that use strong magnetic and electrical fields to make the particles move so fast. Exactly right. All right, so now can you explain the difference between I cannot pronounce it right, so we'll say Becquerel and Curie as units of measuring radioactivity. So what were those? So they're both units of radioactivity, but they're just sized a bit differently. So maybe the Becquerel one is just 1 disintegration per second, while the Curie is going to be quite a bit larger, but it's based more off of a standard, and that one is going to be right here. It's going to be it's going to be the 3.7 times 10 to the 10 disintegrations per second, which is the rate of decay of 1 gram of radium. So it's basing it off of the standard of radium instead of just a number that makes sense. So what isotope of carbon is used for carbon dating, and what is its estimated half-life? And y'all can take a second to write the other down if you need to. So with that, we're typically going to use C14, and that half-life is equal to, or is 5,700 years. Oh, whoops. So why do you think we use carbon isotope dating instead of, what's to stop us from using a different element? So carbon 14 is found In all living things, um, plants end up getting it through like the sun and CO2, and then animals eat those plants, and that's where they get their source of it. So every living thing is going to have carbon-14. So we can use that for everything. And but once they die, they're no longer going to be getting more carbon-14, so it's going to start to decay. So it begins to decay when they die. So it's just a really good standard because it's found in every living thing, and every one of them is going to start decaying at the same point of death. What order process is radioactive decay? So it's going to be a first order process. And then because it's a first order process means that this equation is going to work well with that. I can give you that. So this equation we're going to use throughout these problems that we're going to work for the rest of this worksheet. So if the half-life of zinc 71 is 2.4 minutes, and if one, actually, let's take a step back real quick. So, and look at like what these different variables mean before we get started in this. So in what Dr. Bell used in his videos was he used A for these, but in your PowerPoint, they used N, so it could be either one. And you can either put in that, like for A or in there, you can either put the amount of something that was present initially and after a certain amount of time, or you can put the rate at which it's decaying at a certain point and after a certain amount of time, because the rate of decay is slowly going to decrease because it's decaying a half of it over a certain amount of time. Well, that what a half of it is going to decrease throughout time, so it decays at a slower rate. K is actually going to equal K is equal to the natural log of 2 over the half-life. Or you can also look at that as you can just get rid of this and just remember what that number is, and that's going to be 0.693 over the half-life. That's what K is equal to. And then T, oh shoot, T is going to be T is just the amount of time that has passed or that you're looking at. So it'll be the same number here that A of T or N of T is here. And you need to make sure that the unit is the same for the time as it is for the half-life that is here, because you want those to cancel out. Okay. Sorry about that. Okay. So looking at this again, so the half-life of zinc is 2.4 minutes. And if one had 100 grams at the beginning, how many grams would be left after 7.2 minutes had elapsed? So we're going to be using this equation. Okay, so what can we go ahead and fill in the blanks is what we need to look at. So if we look at this, okay, we know 2.4 minutes is the half-life. And we know that K is 0.693 over the half-life, so 2.4 minutes. Okay. If one had 100 grams at the beginning, how many grams would be left after 7.2 minutes? So it says it has 100 grams initially. We can go ahead and plug that in. And it says that 7.2 minutes have elapsed. So we can go ahead and replace T with that. So now we only have one variable left, so we can go ahead and solve, and that's what they're asking for, is how many grams would be left. So we can just solve for A of T here. So we can go ahead and do our math. And I have that to begin solving it here. I already had part of this problem typed up. Let's see. You have that this first half, if you just solve for this side, it's going to be 2.079. And you had minutes and minutes, so those are going to cancel out. So you don't have any unit over there right now. Okay, so then we're going to take this and we need to get rid of the natural log on each side. So we're going to raise both of them to the power of e. So raise both of them to the power of e. Let's see, those are getting kind of small. Okay, so once we raise both of them to the power of e, we're going to come up with the A over T over 100 grams equals 0.125055. So then we have that. So then we can go ahead and just multiply each side by 100, and then we'll come up with our final answer. And I broke this first one down pretty far so you could see where the different numbers are coming from. So hopefully you won't get confused with that. And then get our final answer of A over T, or not A over T, A sub T is going to be 12.5, or I went ahead and rounded it to 2 decimal places, or not 2 decimal places, 2 sig figs. And so I rounded it to 13. Whoops, I did the wrong thing. That's okay. Let's fix it. So, okay, so we have that. Any questions with that? Or are you guys good? So next, we're going to look at after 24 days, 2 milligrams of the original 128 milligram sample remains. What is the half-life of the sample? Okay, so we're going to start out just the same as we did before. We're going to plug in what we know. So let me just make it real quick. Make this easier. Okay. Okay. So we're going to plug in what we know. That might not work. We're going to try it again. Okay. So after 24 days, so we know what T is. That's our time. 24.0 days. We have 2 out of the 128 milligrams left. So we can put that in here. We have 2.00 milligrams out of 128.0 milligrams. All right. So, and we want to know what the half-life is at the end of this. And so K is not our half-life, remember, but we do know that K is 0.693 over the half-life. So we can go ahead and solve to figure out what we've got going on here. So let's do the left side of that first. So if we take the natural log of 2 over 128, what are you guys coming up with? You've seen one example. So what are you coming up with for this left side? Negative 4.15. Perfect, perfect. So yep, negative 4. I'm gonna put 159 just to have a little bit more accuracy there. And then, so we're gonna have that, and we need to get, we're wanting to get T 1/2 by itself. And so right over here on this side right now, whoops, it's on the bottom of the equation. So what I'm going to go ahead and do is I'm going to multiply both sides by T 1/2 by the half-life here. And then I'm going to divide both sides by this so that we end up with T 1/2 by itself, and then all of our numbers end up on the other side of what we've got left here. So that's going to end up with us having T 1/2 is going to equal negative 1, or not 1, 4.159 times negative 6.93 times 24 days. So what do you come up with for the rest of that? Oh, wait. Sorry, this is supposed to be divided. Get that out real quick. Sorry about that. Okay, so now what do you come up with for the rest of that? Negative 3.99. Perfect, perfect. So we're gonna have, and that's gonna be our final answer. So I got negative 3.999 and then some other numbers. So we're just gonna go ahead and round that to 4.00 days. And then up here, you can see our milligrams cancel out. I didn't do that earlier, but you can see that. Okay. So 4 days, and that answers the question. Our half-life is 4 days. How long, oops, how long will it take a sample, sorry, got my chat box in the way over here. I can't, it's not wanting to move for me. You all let me know if for some reason you can't see the worksheet we're working on at some point. My computer keeps acting weird. I apologize. Okay. So how long will it take for a 40-gram sample of iodine 131 half-life of 8.040 days to decay to 1/100th of its original mass? Okay. So we're going to take our equation just like before. Okay. And I'm going to try this. So we've got our equation, and we can figure out what we can substitute once more. So it's going to have, so let's skip this 40 grams for a second. I'll show you why in just a minute. So we see that the half-life is 8.040 days. Okay, so we can go ahead and fill in what K is. So 0.693 over 8.040 days. Okay. And then they tell us that they want to go to 1/100th of the original mass. So because you needed both parts of this in the same unit, you would end up putting in, if you put in your 40 grams for the original, you'd have to go multiply it by 1/100. So you move your decimal twice. So you have 0.400 grams. And you put that on top. Or you can just go ahead and put in this fraction here, and that's going to be the same thing. So I can just come put in 1/100 for the whole thing, because we're going to have one part of 100%, so that will work. So 1/100. So now we have to solve for t. So if you just want to do everything all at once and not have to do a bunch of steps, we can go ahead and take all of this If that doesn't work for you, then don't do that. That's perfectly fine too. So we're gonna have all this, and we're gonna divide both sides by negative 6.93 divided by 8.040 days. And so then we just have t by itself on this side. So we're gonna move our equals over here, and this is gonna become division. Okay. So let me know what you come up with, and if you guys are struggling with that, then we will, we can break it up further if we need to. Let me know what you come up with when you get there. Take your time though. That's not what I came up with. Try it again. I can go ahead and break this down further if we need to. Because, so you're looking at time, so there's no way it should be negative. And here we go. Actually, here, that's fine too. Let me put it on. Okay, so let me break it down step by step a little bit for you guys and see what you guys are getting. So what are you getting for the natural log of 1 over 100? Let's do that part first. Negative 4.6. Okay, perfect. Yep, that's what I can come up with too. So negative 4.6. Okay. So then we're going to divide that by this. So what are you coming up with for this part here? So divide by what? So what is this going to equal? So yes, the part inside the parentheses will be the 0.086, but don't forget your negative on the outside here. So that's going to be negative 0.086. Okay, so then when you solve this, what do you get for that? 53, cool. 53.5. I had 53.42, so it wouldn't quite round up, but I didn't round my numbers, so that could be the difference. Which that shouldn't be a problem on your exam, so you're okay. So 53 point, and 3 is our smallest decimal places, so let's go ahead and use that. So 53.4 is what I came up with. And then that's going to be in days. Perfect. Cool, cool. Any questions, or are you guys good to go? All right, so our last one here is going to be fermium-253 has a half-life of 0.334 seconds. A radioactive sample is considered to be completely gone after 10 half-lives. How much time will elapse for the sample to be considered gone? So, sorry, my computer's trying to freak out on me again. I'm not sure why it's doing this right now. So our okay, so it's got half-life of 0.334 seconds. That's not gonna let me do that. Cool. Right here. And give me just a second. My screen went black on me again. Here we are. Okay. And a radioactive sample is gone after 10 half-lives. So how much time will elapse for the sample to be considered gone? So we have a half-life, and we know how long it's going to be for 10 of those. So literally all we're going to have to do this time is multiply the amount of time that they have given us times the half-life. So for that, we're going to have the time, so 10 times the half-life, so 0.334 seconds. And that's going to equal what? Oh. 0.334. Perfect. Or it's not 0.334, 3.34. I said the same number. Again, 3.34 seconds. So you can see that we have an incredibly short half-life that we couldn't even really measure because it's gone almost instantly. 3.34 seconds. That's not long at all. So that shows you how unstable that fermium-253 would be and how quickly that would decay, which I'm not sure these numbers are accurate, so it might not actually be true. But for this point of this, you can see that. If you have any more questions, I'm happy to help. But aside from that, that's all I've got for you today. So feel free to ask any questions if you do have it. I'm going to go ahead and end my recording.